And then I put a question up here that was similar to one of the questions on the Coulomb's law check yesterday. So put the following in order of increasing attraction between the valence electrons and the protons in the nucleus. So increasing attraction means we're going to go from least attraction to most. So for 4 and 5, we're going to be putting it in order of least to most. So we're focusing again on the valence electrons and where the protons, or how the protons are attracted to those valence electrons. So first, if we look at aluminum, phosphorus, and chlorine. So all of them are in N equals 3. So in aluminum, phosphorus, and chlorine, the nucleus, N equals 1, N equals 2. All of the valence electrons are somewhere out here in N equals 3. When you're in the same row, we want to look at the number of protons that are in the nucleus. So aluminum has 13, phosphorus has 15, chlorine has 17. The more protons, the more positive charges, the more it's going to pull the electrons in. So chlorine will actually have the highest attraction. Aluminum will have the least attraction. So aluminum, then phosphorus, then chlorine. Because again, the more protons in the nucleus, the stronger the attraction to the valence electrons. So chlorine has 17 protons in here, so it's easier for chlorine to pull those valence electrons in. Then number 5, we have fluorine, chlorine, and bromine. So those are all halogens. They're all in group 7A or 17. In this case, our valence electrons are in different energy levels. So fluorine, it's in, oh, that should be a circle, it's in N equals 2. Chlorine, it's in N equals 3. And bromine is in N equals 4. So now we're looking at distance. So the further away the valence electron is, the harder it is for the protons in the nucleus to attract those valence electrons. So bromine will have the weakest attraction. Fluorine will have the most. Because notice how close the valence electrons are to the nucleus. So then chlorine will be in the middle. So again, there's always 2 things that we'll look at. We'll look at protons and we'll look at distance. We're going to talk about that a lot more today as we look at periodic trends. Okay, so 4 and 5, we just put them in order. But again, we'll talk about that more today. So again, if you want the slides for today, there's this short link, bit.ly/trends slides. And that will open up the periodic trends Google Slides that I'm going to actually just go through right now. So I'll give you guys a second to open that link if you want. Again, you don't have to. I just figure it's going to be easier for most people just to kind of follow along with the slides. And again, if you want to go to File, Make a Copy, that's going to make your own copy of these, so then you can just, make yourself a note in your notes packets that you can always reference the slides as well. So the first slide should look like this. Or if you go to the Do Now slides, you can actually go down. I think this starts on slide 37 or 38. So if you open the Do Now slides and you just go all the way down to slide 37 or 38, you'll see these 2, because I put all of these slides into the Do Now. So either one, or it's also on the website. If you go to ptapchem.com and you click on Unit 1 and Chapter 7, you'll see these slides right there as well. So they're in a few different places. So before we actually jump into periodic trends, I just want to talk about one thing that we should be looking at as we answer free response questions. So tomorrow, we're going to be doing practice free response questions. So you're going to see actual AP Chem style free response questions related to periodic trends. Every time you answer a free response question that's related to periodicity or periodic trends, there are always three things that you want to look at. First, find them both on the periodic table. So you want to find them both on the periodic table, and you want to say the principal energy level and sublevel where the valence electrons are. Because we're always focusing on the valence electrons compared to the protons. So then you're looking at, okay, do they have the same or different n values? Remember, n is the energy level. So n equals 1, n equals 2, n equals 3, n equals 4, so on. Just like with the electron configuration. If they have the same value of n, that means that they're in the same row. Same value of n would be like aluminum, phosphorus, and chlorine that we looked at. They're all in n equals 3. So if they're in the same row, we want to use effective nuclear charge, or the number of protons in the nucleus, as our reasoning for any periodic trend. No matter what periodic trend it is, we use the number of protons in the nucleus, and we can explain the trend. If they're in different energy levels, so that means that, for example, like the halogens, fluorine, chlorine, and bromine, you have n equals 2, n equals 3, and n equals 4. So if they're in different values of n, that means you're probably looking at atoms in the same group. Then we're going to argue based on distance. So distance between the protons in the nucleus and the valence electrons, and how it affects the attraction. So we're still talking about the attraction between the protons and valence electrons. It's just what are we using as our justification. This is probably the biggest thing, and I say it every year because it seems like people always miss the justification part. Okay, so a trend is an observation that we make. It's not an explanation. It's not a way that we justify an answer. So if you say, well, ionization energy increases as you go up and to the right, that's just an observation. You're not telling me why ionization energy does that. So you want to make sure that, and we're going to look at lots of examples of justifications as well. So kind of going on with this, arguments for periodic trends. If you're using effective nuclear charge, you're looking at two atoms that are in the same period or same row. We always are going back to Coulomb's law. Coulomb's law was the most tested topic 2 years ago, and a lot of students last year, and the test was a little different last year, but a lot of them said they saw Coulomb's law as well. So we always want to go back to Coulomb's law. Coulomb's law is just how do the protons in the nucleus attract the valence electrons? Do you have more protons? That's more attraction. Or are they further away? That's less attraction. That's basing it on Coulomb's law. So if we use effective nuclear charge, as we move across a period, the number of protons in the nucleus increases, which increases the force of attraction between the nucleus and the valence electrons. That's the type of justification that we're looking at. If we're using distance, further away you are, the less attraction. You use that when you're looking at atoms in the same group, right, or same column. If we look at it based on Coulomb's law, as we move down a group, valence electrons occupy an energy level farther from the nucleus. Due to the larger distance, the force of attraction is weaker. So notice we want to be as specific as we can. We want to talk about how it affects the attraction, why it affects the attraction. So those are really our only two arguments for periodic trends. Every single periodic trend. So with atomic radii or atomic size, so what I tried to do on here is show the trend and then explain both, and for some we'll look at examples as well. So for atomic size, your trend, it gets bigger as you go to the left and down. So francium, down in the very bottom corner, 7s, that's going to be the largest atom. You notice helium up here in the corner. I know we have hydrogen, but we have helium up here in the corner. Noble gases we typically ignore, so we'll always say fluorine will be the smallest. Right? In reality, it's helium, but we ignore our noble gases, so we'll look at fluorine. So as we go down a group, here's why atomic size increases. As we go down a group, the atom is larger as the valence electrons occupy a further shell from the nucleus. So the valence electrons are occupying an energy level It gets farther and farther and farther from the nucleus, making that atom larger. So as we go, I guess if we're going left to right, across, the atom gets smaller. It gets smaller because there are more protons in the nucleus. There is a higher effective nuclear charge. That's what that's saying. Whichever way, whichever term you want to use is up to you. But the atom is smaller as we go left to right because there are more protons in the nucleus, which increases the attraction to the valence electrons that occupy the same energy shell or energy level. So notice how we state what is true. We give our reasoning, either protons or distance, talk about how it affects the attraction, and because they're either in the same energy level or they're in different energy levels. So we just want to make sure that we are as specific as possible. So here's some examples, and this is why I said it's useful for you to have these slides, because this has example questions and example answers. So for this, one example, and you guys are going to be doing practice in class as well, but which is larger, an atom of Ca or Mg? So if we actually look at it, an atom of calcium, look at our periodic table, if we compare where they are, they're in the same group, so we should be using distance as a reasoning. So an atom of calcium is larger since the valence electrons of calcium occupy the 4s sublevel, which is farther on average from the nucleus than the 3s sublevel, where the valence electrons of magnesium are located. Compare them. So here's a quick how to answer. So answer the question. So state which is larger, which is smaller. Be specific. Don't say it. Make it easy to grade. Then state the location of the valence electrons for both substances. You want to look at the valence electrons for both substances and then list specifics of both atoms. So then if we're looking at the other example, which is larger, an atom of calcium or potassium. So if we look at that, we notice they're in the same row. Right, so which is larger? So we want to make sure that we're answering which is larger. So K is larger, right? Ca is smaller. And Ca has more protons, which increases the attraction to the valence electrons that are located in N equals 4 for both atoms. So again, you're looking at valence electrons compared to protons. Okay, so then ionic size. So I have a couple slides for ionic size because this is where I had a lot of questions. So to start, remember that cations are positive ions. Metals form cations. Metals want to be positive. When metals lose electrons, they are losing their valence shell. They are losing the electrons from the valence shell from the outermost energy level. So when they lose those valence electrons, that causes the cation to actually be smaller than the original atom, or the parent atom. The parent atom is just the original. So if it's Na+, the parent atom is Na, or the original atom. So notice that all of the cations are smaller than the original because they're losing their entire valence shell. Anions, non-metals, form anions. Anions are when electrons are gained. So as electrons are gained, you're putting more and more electrons into a sublevel. Electrons want to repel because they're negative. Bring two negatives together, they want to repel. This is the only time we're using our justification of electron repulsion, is explaining why anions are larger. Because as you add more electrons, the electrons want to repel, so they want to spread out. You'll notice that I have the cations and the anions labeled separately because we have to split the periodic table when we're looking at cations and anions. Because if you notice, right, the sizes do differ between cations and anions. Now, one additional thing with sizes of ions is the term isoelectronic. So, isoelectronic, iso means same, electronic for electrons. So, isoelectronic means same number of electrons. So, there are times that we will look at isoelectronic series. They all have the same number of electrons, but you might have anions, neutral atoms, cations. When it comes to an isoelectronic series, we can remember that the more positive charge, the smaller it's going to be. Because the more positive charge more than likely means there's more protons attracting the same number of electrons. It's going to pull it in. So for isoelectronic, just remember typically the more positive charge, the smaller it will be. And then whether it's a cation or an anion, again, you have to split it up. The trend still follows atomic size. So if we're just looking at cations, notice the trend still follows atomic size. Same thing with anions. The trend still follows atomic size, but we do have to split them up. So again, kind of summarizing the trend. So if the ions are in the same group, ion gets larger as we go down the group for the exact same reason as atomic size. The valence electrons occupy an energy shell that's farther from the nucleus. If they're in the same period, this gets challenging. If you remember the more positive, the smaller it is. You'll be okay when it comes to ordering that way. And then if different ions are being compared, just remember the more energy levels, the larger the atom's going to be. And then the more protons, the smaller it will probably be, so if they're in the same shell. So then, there are actually two slides of examples when it comes to ions. So if we look at this example, which is larger, an ion of Ca2 plus or Mg2 plus. So again, even though they're ions, look on the periodic table. Ca2 plus versus Mg2 plus. Well, when magnesium loses its two valence electrons, it's going to become the same configuration as neon. So its valence electrons are now in 2p. When calcium becomes an ion, it has the same configuration as argon. Its valence electrons are in 3p. So then we still are looking at atoms that are in different, or I guess ions now, that are in different rows. And so Ca2 plus is actually going to be larger because the valence electrons occupy n equals 3, which is going to be farther than n equals 2, which is where magnesium's valence electrons are. Here's the biggest thing with this question. Please remember that if you're focusing on ions, make sure you're talking about them as ions. Calcium's valence electrons are no longer in n equals 4. It's no longer in the 4s because it's lost those 2 electrons. So they're now in the 3p. So just keep that in mind. And then it gives you another example, Ca2 plus or K plus. So here's where, for us, we can remember the more positive, smaller it's probably going to be. Because Ca2 plus and K plus are isoelectronic. Same number of electrons. They both have the configuration of argon. The more positive, the smaller it's going to be. But that can't be our justification. It helps us when we're trying to order them, but that can't be our justification. Our justification is that because they're isoelectronic, they have the same number of electrons, calcium has more protons. So since calcium has more protons pulling on the same number of electrons, it's going to make the ion smaller. Okay, so that looks at, and then there are 2 additional, so ions of different elements. So now we're looking at K plus and Cl minus. So again, you have K plus and Cl minus. Those are isoelectronic. For isoelectronic series, look at the number of protons, because the more protons, the more it pulls in those electrons. Then Cu2 plus and Cu3 plus. Well, now we know that they have the same number of protons because they're the same atom. But then we're looking at how many electrons are they pulling in. The fewer electrons they're pulling in, the more tightly attracted they will be. Okay, so Cu3 plus, again, that follows the more positive, the smaller it is. Okay, so ionization energy. So one thing before I get into ionization energy. There are some exceptions for ionization energy. You want to know them for mastering, just in case you see them. The exceptions are that when you are removing from the P1, so 2P1, 3P1, 4P1, you will notice there's a drop in energy because it's being removed from the P sublevel. P electrons are held a little bit less tightly because they're a little bit farther away from the nucleus. And then when you're pairing electrons, there's an increase in electron repulsion, so it actually requires less energy to remove the electron. So there are two exceptions you need to know for mastering. You will not be tested on the exceptions or quizzed on the exceptions. But you will want to know them for mastering. Ionization energy is the most tested trend that I have seen on the AP test. They love asking questions on ionization energy, both multiple choice and free response. Ionization energy is the energy required to remove an electron. First ionization energy is the energy required to remove the first valence electron, and then second ionization energy is second electron, third, so on. So for ionization energy, we're going to look at some examples tomorrow that actually look at how can we tell whether there's 1, 2, 3 valence electrons based on ionization energy. We will look at that tomorrow. For now, we're just going to focus on the trend. So I know this says decreases as you go down, so I'm going to draw this arrow so that way it makes more sense to us. Increases as we go up, increases as we go over. So francium has the lowest ionization energy. A low ionization energy means it's easy to remove that electron. Fluorine is going to have a high ionization energy. It's hard to remove an electron. So as we go down a group, the ionization energy is smaller. Again, as we go down a group, ionization energy is smaller because the valence electrons occupy an energy level that's a lot farther from the nucleus. So the farther away from the nucleus, the easier it is to remove, because the protons aren't holding those valence electrons. So an example, and I forgot to bring money in my pocket, but an example that I always use is if I had a $20 bill and it was in my pocket. It's really close to me. It's easy for me to hold on to that $20 bill. So the closer the valence electrons are to the nucleus, the harder it is to remove. If I put that $20 bill in the back of the room, you guys could easily go take it because it's a lot further away from me. I'm not holding on to it as tightly. And so the farther away the valence electrons are, the easier they are to remove. As we go left to right across a period, the ionization energy increases as we go across because there are more protons in the nucleus, which increases the attraction to the valence electrons, makes it harder to remove. Notice that every trend so far, we're looking at distance, number of protons. Every trend, that's what we look at. Distance or number of protons. Then we have electronegativity. So we will talk much more about electronegativity when we look at bonding. But electronegativity and electron affinity are very similar. Electronegativity is looking at how easy it is for an atom within a molecule to attract an electron. Now, within a molecule is the most important thing. So when we're looking at electronegativity, we're looking at an atom that's within a molecule, so it's already bonded to something. The trend for electronegativity, as we go down a group, electronegativity decreases. So the arrows for electronegativity look just like ionization energy because the harder it is to remove an electron, the easier it is to attract. So as we go down a group, the electronegativity decreases because the valence electrons are farther away from the nucleus. So they're in an energy level that's farther from the nucleus. So the farther away from the nucleus, the harder it is for that nucleus to attract an electron. Right, so if I'm the nucleus of an atom and you put a $5 bill on the back lab table, it's a lot harder for me if I'm staying here to grab that $5 bill. You put it on this desk, it's a lot closer, it's easier for me to attract that $5 bill. So the farther away from the nucleus, the harder it is to attract an electron. As you go left to right across a period, electronegativity increases because as number of protons increase, it's easier for the nucleus to attract electrons. Fluorine is the most electronegative atom. Okay? We don't worry about noble gases, because noble gases don't attract electrons to themselves. Fluorine is the most electronegative. Francium is going to be the least electronegative. The only difference between electronegativity and electron affinity is that electron affinity is looking at adding an electron to a neutral atom. So electron affinity is actually a newer trend within the AP Chemistry curriculum. So we're looking at how much energy is gained or released when we add an electron to a neutral atom. We actually see that electron affinity for something like fluorine is going to have a negative electron affinity. That's good. That means the energy is released. It's an exothermic process. So negative values are good. The more the negative value, the higher the electron affinity, because the more the attraction. But follows the same trend as electronegativity. Fluorine is going to have a high electron affinity. It's going to want to attract electrons to itself. Francium will have a low electron affinity. The exact same reasons as electronegativity, except now we're looking at a neutral atom instead of an atom within a molecule. So all of the trends looks like this. Now there was a question that said, can I draw this on my periodic table if I use it for quizzes? Well, preferably no. But I know that you have most of you kept the white periodic table from the very first naming quiz. So if you want to color code that, or you have another periodic table that you use often, you can add this to your periodic table. So notice that ionization energy and electronegativity, as well as electron affinity, all point the same way. Size is the only one that's opposite. So francium is the largest atom, but also has the lowest electronegativity, the lowest electron affinity, and the lowest ionization energy. So then just another visual, because I did talk about metallic character. Here's the thing to remember about metallic character. This side of the periodic table is metals. They have high metallic character. Francium actually has the most metallic character. Fluorine has the most non-metallic character. You're just looking at metals like to lose electrons. So because francium has the lowest ionization energy, it's the easiest to remove an electron. So it's actually the most reactive metal. Fluorine has the highest electron affinity. It's easiest to attract electrons to itself and become an anion, so it has the most non-metallic character. So this is probably one of the most important slides on here. This is actually looking at sample responses to periodic trend questions. So they give different responses and why it's incorrect, and then how to make it better. So this first one says magnesium has a higher ionization energy than sodium because the outer shell is full as opposed to half filled. We don't worry about full outer shell, half filled shell based on ionization energy. We are looking at how many protons are there in the nucleus and how far are the valence electrons away from the nucleus. That's what we focus on. All right, so here's another one, and this is a very common response. Magnesium has a higher ionization energy than sodium because magnesium is a smaller atom than sodium. Right? You can't use a trend as a reasoning. You need to use one of two things, and I have it down here. I have one of three things, but it's usually one of these first two. You have to tie it to Coulomb's law. Coulomb's law is how are the protons in the nucleus attracted to the valence electrons? So you either talk about number of protons and how that affects the attraction, or distance from the protons to the valence electrons and how that affects attraction. And then the electrons repelling we use when we look at anions. Okay, so then another response, this response is not correct because you need to make sure you're talking about why attraction increases or decreases. So not only are you saying you're increasing your number of protons, but then talk about how that affects the attraction. All right, and then finally, one looking at ions. All right, so I said it's easy for us to remember that positive is smaller than negative, right? Cations are smaller, but that can't be our reasoning. So our reasoning has to look at protons compared to the location of the valence electrons, especially for isoelectronic series. All right, so that just shows some common responses and how we can make them better.